Welcome to Yaka Digital Network. Today, we are mastering moles and equations. These exact calculations drive Ugandan industries, from large-scale agriculture to municipal water treatment. To safely disinfect a district's water supply, a treatment plant relies on precise measurements of chlorine. To achieve that precision, technicians use equipment like this mass spectrometer to measure atomic properties directly. This graph shows the mass spectrum of a natural chlorine sample. You'll notice two distinct peaks at mass-to-charge ratios of 35 and 37. Because chlorine exists as these two different isotopes, the relative atomic mass you see on the periodic table isn't a simple whole number. We have to calculate a weighted average. To find that average, we take the mass of each isotope and multiply it by its natural percentage abundance. For chlorine, the mass 35 isotope makes up 75.77% of the sample, while the mass 37 isotope makes up the remaining 24.23. We multiply those values, add them together, and divide by 100. The result is 35.5. If a chemical engineer ignored those decimal points and used a flat whole number, scaling a reaction from atomic units to industrial tons would produce massive, costly measurement errors. Accuracy at the atomic level ensures safety and efficiency at the industrial level. Consider a local fertilizer plant producing ammonium sulfate. When working with raw materials at this scale, efficiency is tightly controlled. This split screen shows our reaction. On the left is the balanced equation. 2 moles of ammonia react with 1 mole of sulfuric acid to produce 1 mole of ammonium sulfate. On the right, we have a starting batch of 34.0 kilograms of ammonia and 78.4 kilograms of pure sulfuric acid. Pause the video here and determine which chemical is the limiting reactant. A quick warning, do not fall for the trap of simply picking the reactant with the lowest starting mass. You have to compare mole ratios. To solve this correctly, we first convert the starting masses into moles. That gives us 2,000 moles of ammonia and 800 moles of sulfuric acid. Next, we divide each amount by their equation coefficients, 2 for ammonia and 1 for sulfuric acid. The smaller resulting value tells us that sulfuric acid is actually our limiting reagent. Identifying the limiting reagent accurately is a mandatory step. It determines the absolute maximum yield the plant can produce from a batch, which ultimately dictates the operation's efficiency and profitability. Moving from large-scale manufacturing to the quality control lab, chemists routinely standardize solutions and titrate unknown alkalis. Here, precision liquid volumetric analysis is built on the relationship that moles equal concentration times volume. This visual shows the standard titration formula. Notice the N in the denominator. You must apply the stoichiometric mole ratio from your balanced equation to find the concentration of an unknown. You cannot assume the moles are equal without checking the balanced equation first. Those same principles of stoichiometry apply to gases, like when capturing rural biogas. To calculate the exact amount of methane gas collected, we use the ideal gas law. Pressure times volume equals the number of moles times the gas constant times temperature. The most common error students make here is ignoring the units. For this equation to work with the standard gas constant, your pressure must be in pascals, your volume in cubic meters, and your temperature in Kelvin. Before plugging any numbers into the formula, we execute precise conversions. A pressure of 100 kilopascals becomes 1.00 times 10 to the 5th pascals. A volume of 2.50 cubic decimeters converts to 2.50 times 10 to the negative 3rd cubic meters. And 25 degrees Celsius requires adding 273 to reach exactly 298 Kelvin. Mastering these specific unit conversions and stoichiometric ratios removes the guesswork. It allows chemists to confidently predict and control reactions across solids, liquids, and gases. This flowchart illustrates how everything connects, moving from raw mass to moles, through the balanced equation, and branching to gas volume or solution concentration. These steps solve complex stoichiometric problems. Here is a final review of the core formulas. Take a screenshot for your study notes. You now possess the analytical tools to solve advanced, real-world chemical problems. To practice these calculations and access the full syllabus, visit the Yaka Digital Network website on your screen.